just a bit. And by differential geometry, you should think studying surfaces or curves in 3 space by way of derivatives, right? That the idea here is to study geometric properties that a function has by looking at its derivatives. So differential geometry is the study of curves and surfaces with vector derivatives. And so some of these ideas you would have seen before, hopefully. So we're going to go back through, I think, what is typically not a well-described part of Math 241 if you took it here, Calculus 4 if you took it elsewhere. And if you have never seen this stuff before, this will be a non-theoretical, but like at least intuitive explanation of where the ideas of this 3-dimensional geometry actually come from. So the first question that we might ask is, I have some, imagine you got some path x of t. So this is a path. And let's say it's a path of a particle moving. It doesn't have to be, but it's a useful analogy to make, right? So you have this path sort of twisting through 3-dimensional space. And let's say that x is defined from A to B. So there's a beginning point and an end point. So one question you might ask is, if you saw the particle moving, there would be quantities you could associate with the motion of the particle that would be dependent on how it was moving, right? If you had a moving particle on this path, so say on this path there's a particle that is located at position x of t, and it's sort of traveling along the curve this way, you could say something about the velocity of the particle or the acceleration on the particle, right? These are physical ideas that you could, or mathematical quantities you could associate to the particle as it moved. And particles, say, moving at different speeds would have different quantities, right? You could imagine this could go twice as fast, and then all the velocity vectors would be twice as long. Frequently, though, we don't care about the particle doing the path. We just care about the path itself. If I don't want to analyze, or if I don't want to analyze how the particle is moving on the path, but just what it traced out when it did it, right? The trail that it left behind. So I think of the curve. The curve is the range of a path. So the curve is just, what did it do? If it's covered with paint, and left a paint trail behind, or had smoke coming out the back, and it finished, and you didn't see it move, you could still see the path that it left behind, or the curve that it left behind. And it wouldn't matter how fast it did it, or if it did it forward and then turn around and go backwards again. Like, there are things about this curve that don't depend on how the particle moved when it made the curve, right? So an example here that you might think is sort of an example that irritated a bunch of students when I taught 241, but the book loved, was this one. What is that? Well, if you do a simple change of variables, so this is a path. It's a path, and I could define it from, say, minus 2 pi to 2 pi. So we define f to be a path from minus 2 pi to 2 pi into r. R2. Well, because this, if you think about this as being x, this is x squared. So this is a parabola this is traveling. Whatever is in this entry, if the square is in the y entry, the x coordinate is always cosine t, and the y coordinate is always the square of that. It turns out to be the case that what you get is, starts at negative 2 pi. What's the cosine of negative 2 pi? 1. Okay, so it starts here. X is 1 and the square of 1 is 1. And then it travels backwards until it gets to minus pi, where the cosine is negative 1. And then it turns around and goes this way again. And then it turns around and goes this way again. And so it sweeps out a parabola but it's periodically bouncing back and forth from the point 1, 1 to the point minus 1, 1. And the question is, okay, we might want to study how the object is moving, but maybe all we care about is the parabola itself, the curvature of the parabola, or the derivative of the parabola, not how the actual object moved, but the path or the curve that it left behind, the trajectory of the object. Okay, so quantities that are related to the curve, but not the motion of the particle, are called intrinsic qualities. So an intrinsic quantity is related to the curve, not the path. Which means I could double the speed and the quantities don't change. I could triple the speed. I could bounce periodically. The curve doesn't change. And in earlier classes, what you would have learned is that intrinsic qualities include things like curvature. Curvature is a quality of the curve. Actually, does anybody remember? I'm curious. Don't tell me an equation for the curvature. What does curvature mean? I know it tends to get ripped through in the multivariable calculus class the first time you see it, right? Okay, so second derivative is a reasonable way of thinking about what it is, right? So you can think about curvature in some sense as measuring how quickly a curve is bending, right? So it measures acceleration. It's loosely associated with acceleration, but acceleration would be a non-intrinsic quality because you're going to have different acceleration if you move different speeds. So curvature is sort of like acceleration, but with velocity deleted from the picture. Curvature is a quantity that measures how much this thing is turning at any point in a sort of velocity-free way. On the other hand, you have, so this is intrinsic. I'm going to define these things, don't worry. And extrinsic, I should say non-intrinsic, the acceleration. Another intrinsic quality you guys would have learned would have been, I'm going to remind you, again, I'm just trying to jostle your memories before we go in to start talking about these things. A unit tangent vector. So the unit tangent vector tells you what direction the curve is headed, but it has no magnitude, right? You delete magnitude away. If you just have a unit tangent vector, what we're saying is, oh, at this position right here, there's this vector of length 1 called t, and it's a unit vector. Unit vector means it's not keeping track of what x is doing. It's keeping track of the direction x is moving, but it's not keeping track of how quickly it's doing it. Unit tangent you define to be, we're going to get here as x prime over the length of x prime. So you take the derivative of the function, which gives you a velocity vector, and then you delete the speed out. All that's left behind is the direction the curve is traveling. So the intrinsic quality of the curve is the unit tangent, and the non-intrinsic, or the particle version of that, is velocity. So non-intrinsic qualities are associated with how the particle is moving. Intrinsic qualities are associated with the curve that it left behind. And that's kind of what we're going to explore today, is how to relate these ideas, how to use the motion of a particle to say things about the trajectory that it took. Okay. So the most basic question that you can ask about a path or about a curve is, how long is it? So if you had some curve given by x of t, and this is x of a, and this is x of b, I could ask, how long is this? It's a curve floating in space. How long, how much distance did the particle travel? And so the idea here is that, we gotta have derivatives get into the mix. And I don't know if you guys have seen this particular, I'm not going to derive the whole thing, I'm going to give you an idea of how it works. If you take a thing in space, a curve like this, and you cut it up into straight line segments, what you've done is a process called rectification. So rectification just means replacing something curved with a collection of straight lines to approximate. And the idea is, I can actually figure, I can tell you exactly how far apart these points are if I think about the line connecting them, not traveling along the curve, but just what's the straight line distance between two things. If this is x at a point ti minus 1, and this is the point at x ti, then the distance here, you could just compute, subtract, right? The xi is equal to the square root of xi squared delta, change in the x variable squared plus the change in the y variable squared plus the change in the z variable squared. It makes sense? It's just the distance formula. You got an x, y, and z right here, and an x, y, and z right here. Subtract and take the square root. It makes sense? So each one of these line segments has this little distance formula attached to it. Now, I'm not going to belabor this, but what that means is that the length you can think of as being the sum, or about equal to, it's approximated by the sum of all these little line segments. So what you do is you just sum up from I equals 1 to n of all these little line segments. Change in x squared, change in xi squared, plus change in yi squared, plus change in zi squared. Now, every time we have an equation like this written down, what is the move in calculus? What's the calculus move, right? Oh, look, we've written something as little tiny quantities. What are we going to turn it into? We're going to use a limit, but it's going to turn into some sums. When you take a limit, a sum turns into an integral. Except I really want this integral to be in terms of t. And there's no t's anywhere in this. It's just these little changes in x, right? So the question is, how the heck do I get the dt in here that's going to fall out of the integral? It's got to come from somewhere. I mean, yes, the idea, basically the only idea in differentiable calculus is take a limit. And what you're hoping is that an integral falls out. But there's no dt. Right, it's delta t, which would turn into a dt. Where are we going to get one? I'd be impressed if anybody in here remembers how to take little tiny changes in x and force there to be a dt. We're going to do a substitution where we're going to replace this with something it's about equal to. You're going to take a stab at it. The most important theorem in all of undergraduate calculus that basically seems like it's a meaningless technical exercise when you do it. How am I going to replace this change in x with something involving dt? I'll give you a hint. I have a piece of a curve that looks like this. This point down here is x of ti minus 1, y of ti minus 1, z of ti minus 1. And up here, the point x of ti, y of ti. I want to do this. This picture is famous in undergraduate calculus books. It's the mean value theorem. Nice. All right. Yes. Okay. So the idea here is there's some t value in between here where the slope at this point is the same as the slope of this line. So the mean value theorem asserts, for those of you that are coming from a more proof-free environment, you don't need to prove this, but the idea is that if you have a continuous function, that the slope between the endpoints of the function can be approximated by the derivative somewhere in the middle. That's the content of the mean value theorem. So the mean value theorem says, probably you've never even used the mean value theorem in your life before, but what the mean value theorem says is that change in xi is equal to x prime of t star I times change in t. The change in, I mean, I guess really what you're saying here is that xi plus x of ti plus 1 minus x of ti divided by ti plus 1 minus ti is equal to, the mean value theorem asserts that that slope between the endpoints is equal to x prime of ti star for some ti star that's contained inside the interval. And that is actually where we cheat in the dt, right? Because this quantity right here is the numerator of this fraction. And this gets you delta xi is equal to x prime of t star times delta of ti. That might seem like a triviality, but this is a massive move to be able to do this, right? This is why the mean value theorem matters, is that I can do, anytime I've got these secant type approximations, I can always cheat them out and get a derivative approximation in there.
Is that a star right there?
This is a T star. Yeah, it's supposed to be a T star. So I can't specify exactly what that is. But what we're going to do is we're going to make the intervals smaller and smaller and smaller. And the TI star is going to get crushed in by the endpoint. And that's basically the move. Once we know that we have the mean value theorem, and I can do this derivative approximation, I just say this thing is actually equal to the sum from I equals 1 to n of the square root of, we should be a little tiny bit careful here, but it's like delta xi squared plus delta xi yi squared. We're going to use this substitution. So xi star is going to get out, and we're going to get an x prime of ti star squared plus y prime of ti star star. It's a different value of t, but it still lives inside that little tiny interval. Plus c prime of ti star 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 squared. And then where did the delta t's go? Well, the delta ti was squared and squared and squared. So we just factor it out. Take the square root. And that is a classic sort of thing that turns into an integral when you take the limit. You take the limit of this, and what you get is the integral from a to b of the square root of x prime t squared, I prime t squared, prime t squared. That's how we define the limit. So I admit, I went through this kind of quick. The reason is because I don't really want to get into there's a mess of algebra that actually shows that this actually holds. I'm trying to give the idea of what you do. This is just the distance formula. You use the mean value theorem to come up with these useful substitutions, which is where you get the dt. And then you take the limit as the t's get really close to each other, and the result is the limit. Or the limit here, you take the limit as t gets small, and you actually get the thing we call the length. Now,
wait, how did ti go out?
Because when we sub this in up here, this became the square root of x prime of t dt plus y prime of t dt squared plus z prime of t delta t squared. But since that has a delta t squared, and that has a delta t squared, and that has a delta t squared, we can factor it out.
The other two also apply.
They all have, yeah, we basically, it's also the case that delta, sorry, I should have said this expressly here. You can do the same, I said it in words, but on the board, delta yi is equal to y prime of ti double star, but the same delta ti, the same change in time contains the same approximation, and the same thing for z. Now, if you apply the mean value theorem twice, you don't get the same t value each time, but in the limit, since the t's are, you're making the little segments you cut the curve into so small that the t star, the t double star, and the t triple star end up crushed into each other. Yep.
Can you explain that star idea again? Like why are they not the same?
Oh, because I mean, the mean value theorem just says that the change in x can be approximated with the derivative, and also the change in y can be evaluated with the y derivative, which is not the same as the x derivative. Okay. I mean, there's a rigorous proof of this in the book. It's just, I don't think it's actually worth looking at, because the idea here is it's just taking the limit of the distance formula. Yep.
those x of t, y of t, z of t are other functions of the
Oh, indeed they are. They sure look, doesn't that look familiar? I look at that and I say, oh, x prime, y prime, and z prime, those are the component functions of the vector derivative of the path, right? So this could actually be written as the integral from a to b of the length of the derivative. That's our main formula here. If you think about what's going on, if you took the derivative vector, remember x prime of t is equal to x prime of t, y prime of t, z prime of t. I mean, that's the definition of the derivative vector in R3, right? So if you dot that vector with itself, you get x prime squared plus y prime squared plus z prime squared. Well, the length of this vector is square that, square that, square that, add them together and take the square root. But that's exactly what this is. So the formula that we get, sure, a lot of coincidences in vector calculus. The formula we get by approximating the distance formula also turns out to precisely be the length of the derivative of the path. So that's our first major idea. Is that L, length of a path, is equal to the integral from a to b of the length of its derivative vector. You might think, okay, well, why does that make any sense at all? How does it make any sense that length can be recovered with, I mean, this is what we're doing is we're reconstructing the length of the curve somehow by looking at the speed of the path on the curve. That's weird. And sort of unsatisfactory, right? Because that means that length, does it actually matter how a particle travels a curve? Does it change the length of the curve? If I just have some circle and I send a particle around it at 1 RPM versus sending it around, once, right? Oh, go around at 1 meter per second. That's a path X. Send it over 1,000 meters per second. Oh, that's a different path X. Is the length different when you do that? Well, no, it's not. Something's going on here. That means that somehow we've made length, our version of length here isn't quite satisfactory because we've taken something that's intrinsic to the shape of the path that was made, but we're describing it in terms of a quantity related to the specific motion of the particle that swept the curve out. So there's a move. Okay, now this is I have to imagine most of you haven't seen this.
But isn't it the derivative?
Well, X is the path, X prime is the velocity, and then length of the velocity is the speed.
We integrate velocity.
That's exactly what you're doing. Is you're integrating speed, you get length back out again. So it's a reconstruction on that basis. What I'm saying is that's unsatisfactory because I think that's unsatisfactory because yeah, you guys have seen over and over again that the integral of speed is equal to distance, right? That's like a classic idea in calculus. The problem is length is associated with the shape of the curve and not the particle that did it. Yeah, as the velocity increases, you don't change the length of the path that you did it faster, but we're not seeing how fast you did it. We're just saying like, I mean, the A and the B would change in the setup if the path changed, right? Okay, so the question is, how many of you guys have seen parameterization by arc length? That is like one sentence that you're supposed to have spent some time doing that I'm going to. I was just curious if anybody's seen going in. Okay, so the goal is, it'd be nice if we could describe the length of a path in terms of something intrinsic, something that didn't depend on how the particle was traveling. Okay, so I'd like to find a parameter. We're going to call it S. That is intrinsic. That is, does not depend on the speed at which the particle is traveling. Right? I want a parameter S that is intrinsic to the curve to describe length. And so to do that, I'm going to introduce a function called the arc length function. Okay, so for a point P naught,
Can you read that last part again? Curve two.
that would write this. We want a parameter S that is intrinsic to the curve to describe the length of the curve. Basically, I want to replace t, which is a time parameter, with something that's based on where I am on the curve instead. Okay. A point P naught, which is equal to, say, x of a, and a point P, well, define S of t to be equal to the integral from a to t of the length of x prime of tau d tau. See if we can figure out what that does. So you've got some path, and you have a point P naught, which is x of a. And somewhere along here, you've got some point x of t. And what this is doing is this is a computation of the distance. You tell me the time that I'm at, and I will tell you how far along you are along the curve from where you started. So this is a function that for any given time t will tell you how far you are away from some base point. Okay? This is called the arc length function. And what it tells you is the output of S of t. So t takes, S of t gives you the distance along the curve from some base point P naught. In practice, you like to, when you're doing computations with these things, you like these functions because you may actually need to know how far you are for lots of different times, and it's nice to have a function that produces that. Yep.
How is that different from that?
This one has a fixed beginning and a fixed end. I imagine here it's a static object. It's a curve floating in space. It's a fixed beginning and a fixed end. It just sits there. What this one does is it tells you any time you give me, this is going to give you a different output. If you pick the different time, like say, I don't know, S of T2, that might tell you the length out here to X of T2. Any input you give me produces a different length from the base point.
Okay.
That's what it does. This gives it time, it spits out length. So it's a function, it takes in time and spits out length. And the reason we introduce this is actually not because it's often used in practice, but because it actually gives us access to all kinds of tools in terms of this parameter S, because at least in theory, I can solve this thing. I have S of t equal to the integral from a to t x prime of tau. Don't get concerned about the tau in there, by the way. The tau is what's called the dummy variable, just in there so we can integrate it away. What's the derivative of S? Oh, is it x prime t? It's almost x prime t. Length of x prime t.
Oh yeah, that's what I meant.
I figured that's what you meant. Why is that true? Fundamental theorem of calculus says that if you take a derivative of an integral like this, what falls out is what was inside the integral. So ds dt is equal to x prime t. That's going to be important, right? We're gonna be using this. So the idea here, even though it's impossible to do in a practical setting, is that the relationship between S and T given by this function is reversible. I can actually solve, in theory, I can solve this equation for T. This is some mad equation of t's and square roots or whatever like that. But in theory, this could be reversed to give t
It's no longer
as a
tau.
function of s.
It doesn't stay as tau anymore.
What do you mean?
Uh,
I mean, when you integrate, no, by the fundamental theorem of calculus, the fundamental theorem of calculus says whatever's up here, you plug into the function,
oh,
right? So in theory, this gives us a relationship between time and length, right? S of t measures how far along the curve you are. T measures the time that it took you to get there. In theory, that's a reversible relationship. I don't know if I'm like, this is kind of a weird move, but it's important. So I can reverse this in the same way that if I had y is equal to some f of x, many functions you could solve for x and get some crazy function in y out the other side. And if you, in practice, if you can do this, if you can solve for t so that t becomes a function of s by that relationship, then it turns out to be the case that s is what's called the unit arc length parameter. And the reason it's useful from a theoretical standpoint is it doesn't have any velocity attached to it. All it tells you along is how far along the curve you were. S tells you how far did you go. S is a parameter length. So on a curve, if I give you an S value, I'm telling you go out to whatever point, let you get S units away from your base point. S is basically an explicit measure of how far along the curve you went. And notice, nothing about S involves the use of time at all. No time, no velocity, no acceleration. S is a way of just providing a value that tells you how far along you traveled on some specific curve, with no reference to t. So that's why we talk about S as being intrinsic. It's a way of using the length of a curve as a variable to study the curve. This is a reason why this gets glossed over in your calculus classes. The nice thing about S, though, is that you never actually have to do anything explicit with it because you can just use the chain rule. After all, if you have a function that is parameterized not by time, but by arc length, and you want to actually compute with it, well, the derivative with respect to time of f of s is equal to f prime of s times ds dt by the chain rule, but I know what ds dt is. ds dt is just the length of x prime of t. So normally when we're working with these things, the S is a theoretical tool to discover formulas or define them, and the computational version will involve actually computing derivatives using the chain rule. Right. Okay, so what is the point of all this? This is an excellent question to ask every once in a while. The unit tangent vector. All right, let's get away from abstract nonsense here. The unit tangent vector is defined to be the following. T is equal to v divided by the length of v, or if you like, x prime of t over the length of x prime of t. There you go. That's a point right there, x of t. It's got a unit vector sticking off of it called t of t. The unit tangent vector describes the direction the path is going, but not the velocity with which the particle is doing it. We've divided the velocity away. We kept the direction of the velocity, but thrown away the speed. So unit tangents measure direction. Unit tangent.
So at that point where the
Yeah, the unit tangent vector at x of t is defined to be t of t, which is defined like this.
basically like the direction it would be heading.
That's right. The direction it would be heading, but not how quickly it would be doing it. Right? Because remember, we're trying to step away from the fact that the speed with which the particle is traveling measures anything about the curve. right? Well, here's an interesting idea. Turns out there's this other vector. Let's just do this first. Not do the unit normal yet. Let's do the curvature first. So curvature then. Curvature is supposed to be a measure of how quickly a curve turns. And it turns out to be the case that the quantity that you want to use to study that is the derivative of that. So I want you to imagine for a second why the derivative of this vector tells you something about curvature. So the tangent vector is just telling you what direction you're headed, right? As you travel a curve, the tangent vector points forward like this. And as you move, if I take velocity out of the picture, the derivative is measuring how quickly things change, right? But if the velocity never changes, what is the derivative measuring as this tangent vector swings around? It can't be, it's not changing velocity because the velocity doesn't change. So what's changing as the thing swings around like this as I travel some curve? Can I be more specific about what do you mean by, is there a way that we can measure direction that would be useful? Because it's not direction completely, because direction would include something like the length of the vector. Yeah, change of direction measured how? This is a big deal about what this does. The magnitude of the derivative of the tangent vector is a measure, or is equal to, the rate change of, well, again, if velocity is not changing, what is changing? If the speed isn't changing, what's changing? The angle is changing. This measures how fast the angle is changing. So it can't be measuring anything about length because the length of the tangent vector never changes. It's always 1. So the only thing that can be changing is the direction, which is measured by the angle. So the length of the derivative vector is the rate of change of the angle of t. So it's a measure of angular rate of change. Why should that measure curvature? Yep.
What is the angle of t like?
So I want you to imagine instantaneously. So this is an instantaneous quantity, right? So if I have a tangent vector that's telling me the direction I'm pointing, and I take its derivative, essentially what that's telling me is where does it look like in the future my angle is going to be sweeping through as I change? Here's a really good way of thinking about it. I'm on some curve and I compute the tangent vector right here, right? What you're actually doing is something like, if you continued on a circle that was on this path, what would it look like you were doing right here, right? This is sort of what you're measuring is how quickly this angle looks like it's changing. There's some angle here. The faster the angle changes at a point, the harder the turn that it looks like you're going through, right? This, you can think about, there's an angle here that's measuring where it looks like you're headed with this approximating circle. And as you do that, if you were on that circle constantly, then the angle would be sweeping at some constant rate of change, right? If you were on a circle, that would be constant. So what your derivative is measuring is how quickly that angle is changing. Again, even if you take the circle out, the idea is, here's t of t. At this point, t of t would face right here, which would mean that you were looking at an angle like this. As you bring that picture together, how quickly did it look like the angle was changing at that point? So this is a measure of the rate of change of the angle of the derivative of the tangent, or the unit tangent vector. And how does that measure curvature? Well, the faster your angle is changing, the harder you're turning. If you're on a curve like this, and all of a sudden you go like that, your angle is changing pretty damn quick through here, right? Whereas out here, the angle is hardly changing at all. Here, the t values, it's like on my body. Here, the tangent vectors don't really change at all, but then when you're up in here for the same sort of unit time, in the same interval of unit time, you get huge changes in the angle of the vector. And that's what this is picking up. And this is going to be why we want to use this to define curvature. Curvature we can define to be this quantity, because when this is large, it means that or it's going to be involving a quantity involving this. When this is large, we're turning quickly. And when it's small, we're hardly turning at all. Make sense? No. All right, so here's the definition of curvature. The curvature, big definition, the curvature of a path is the angular rate of change. Of the direction of t per unit length. Now, why unit length and not unit time? Because I want to make sure that no matter how fast I'm traveling, that I'm cutting the curve up into equal length pieces, not pieces where the velocity could increase or decrease, but I want curvature to be associated with chunks of the curve, not the particle that's actually doing the motion. So angular rate of change of t per unit length. Okay. K of t. Oh, that's right. We're going to practice. What Greek letters have we written so far in here? Tau, and that's it. Do you guys know? Do you guys know what C looks like? Uppercase C. 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 No, not C. C is easy. I can write C for you. C. No, man, not psi. C. There's lowercase c is the one that math professors use when they want to bother you, like this. But uppercase C looks like this. Look at that monstrosity. That's good. So I just saw a talk that somebody gave. I don't know if I told you guys in the earlier class, but they're in there. Somebody just told me about a talk they saw somebody give where they took this quantity and divided it by its complex conjugate, which looks like this. There's the complex conjugate of C divided by C. Which is, that's my life goal, is to actually do that on the board sometime. Anyway, let's get back to it. Okay, here's a computational formula for the curvature. Kappa of t, that's a crappy kappa, but you guys can practice your Greek letters if you want. Kappa of t is equal to the length of this vector divided by ds dt. This gets the time out of the picture. That's the idea here. So that tells me how quickly the angular change is happening with respect to time. That gets rid of the time and puts the arc length parameter back in again. Because it's the computational formula for this. This is technically the definition and no one ever uses it. The idea is compute how quickly the tangent vector is changing with respect to time, but we don't want velocity to be part of that picture, so delete the velocity and put arc length parameterization in its place. This is essentially just a change. Okay, so what is, actually, I have time to do a quick example. I've got 1 minute. All right, let's do this quick. X of t. You know what? I don't want to do this. X of t is equal to cosine of t sine t. What sort of shape is that? It's a circle. Okay, cool. What's x prime of t? Minus the sine of t, cosine of t. Sweet. What's the length of x prime of t? 1. Sweet. Okay, what's the tangent vector t then? T is supposed to equal to x prime divided by the length of x prime, which is the same exact thing, right? Except then we got to take the length. What's the length of this vector? Sine squared plus cosine squared is? I take the square root and I get. All right, sweet. Okay, so t is constantly equal to 1. You know what? This is stupid.
Oh,
Why am I trying to jam an entire example into 1 minute? It's ridiculous. All right, so what we'll do next time is I'm actually going to start, I'm going to show you guys a little bit about, there's just no reason for this. I'm not going to keep you over. What we're going to do is I'm going to show you guys how to deal with quantities that look like this. So if we define curvature in terms of the path and these quantities, once we have a notion of curvature, we have different notions that we can use to describe the motion. So it's going to turn out to be the case that I can use the tangent vector to define the normal vector, which will measure how much I'm accelerating in the direction I'm turning. So curvature basically is going to tell me, T is going to tell me where I'm headed. N, which is related to the curvature, is going to tell me how I'm turning. And then there'll be a cross product vector, which sticks straight up of the binormal vector, which will tell me how I'm twisting. And this is the basis of differential geometry. So we're going to take curvature and we're going to build it up to a 3-dimensional picture of motion and not just a flat 1-dimensional picture or 2-dimensional picture. All right. So we'll pick right back up here next time.
Is this the